Thank you very much. Thanks for the invitation. It's my first time at this workshop, my first time at Yale. So it's been a wonderful experience and I'm learning quite a lot. All right, so I want to talk today about dynamic MRI. We've already seen some wonderful applications of it from Ricardo and Shun, so I'm not going to spend too much time motivating specific applications other than the fact that it touches quite a lot of areas. Now, in the research community, at least, our dynamic imaging problems are growing larger and larger in terms of number of image frames. And part of that is because the rise of multidimensional techniques such as XD grasp and multitasking that really give us the curse of dimensionality, where our number of image frames is going to increase exponentially with the number of dimensions. We also, our ambitions in frame rate and temporal resolution are giving us more image frames per unit scan time. And so you can really see, you can look through the literature and people are doing in a single scan thousands, tens of thousands, hundreds of thousands of images from a single sequence. So for these really, really large scale problems with lots of frames, low rank factorization and linear subspace constraints have become workhorses for these types of problems. And it's because they can do global temporal modeling with an extremely low memory footprint and extremely low computational complexity. So it's essentially the only thing in some situations that can get you to being able to solve the problem in the first place. Oh, there we go. So just as a quick primer on low rank decompositions, what that means for dynamic imaging, basically it is that if you have a dynamic image, this is a small scale, 30 frames in the sequence of the heart beating, you can actually decompose this into a spatial factor and a temporal factor. All right, and there's only 12 each in this particular case. So there's some mild reduction here in terms of the degrees of freedom. And you can look at this a couple of ways. One, you can look at this as the spatial factor is essentially eigen images for this image sequence, at least when they're properly scaled and rotated. Or if you want to take the subspace view that we're going to end up going with, is that these temporal functions you can usually calculate quite quickly or know them ahead of time, in which case they constitute a linear subspace constraint on your image. And that means that image reconstruction is actually just recovery of that spatial factor. You're trying to recover these L images as opposed to the number of time points. Now, if you squint really hard at that, it actually looks a little bit something like Dan mentioned yesterday, which is that if you're trying to think of image reconstruction as just getting the spatial factor, it is actually being encoded by motion that's embedded in the temporal subspace, because that goes in your forward matrix. And I will confirm that a little bit of irregularity in terms of heart rate and things like that does give you incoherence. So there is some benefit to that. All right, so the pros of using this linear subspace formulation is, as I mentioned, a global temporal model with low memory. And what I really mean by that is that once you go from the time domain to the low dimensional subspace, you never have to leave until image retrieval. So you can do all of your data consistency, you can do all of your sparse coding, you can do all of your processing, spatial encoding, everything like that within the subspace. And then you only decompress it at the end. And so that means that all of your computation is going to be tied to the subspace dimension, not the number of frames. So all you need to know is how complex is your underlying image, get the right subspace dimension, and you get to stay there. Now, the price you pay is that it is not nearly as powerful as any of its nonlinear counterparts. And actually, Matthew's group has shown beyond the shadow of a doubt that nonlinear manifolds, even before we were doing deep learning, it really gets you fewer degrees of freedom, but you do have to pay back, a lot of times, back to the time domain, at least at some point in your processing. So to try to balance that a little bit, when we're doing linear subspace models, we usually pair this with non-Cartesian sampling, which gives us some nice incoherence properties, or do some sort of nonlinear regularization on the spatial factor, which then at least gives us a flavor of that nonlinearity and allows us to reduce our degrees of freedom a little more. So this retains all of our memory benefits, but it does slow down the iterative computation of the spatial factor. So what I want to talk about today is deep subspace learning. Now, there's actually a few different flavors of this and other groups that are working on it. I'm only going to cover how we formulated it, but I do want to give a shout out to the Stanford group who gave it a much better name than we did, deep subspace learning. So I'm going to lean into that. I quite like that. And this is basically where we're going to leverage these matrix decompositions or linear subspaces, and we're going to use deep learning together. So we will retain all those memory computational benefits, and we'll be able to dramatically reduce our network size so that it's operating in the subspace instead of in the time domain. And the deep learning, of course, is what introduces our nonlinearity. And it could be a number of ways, and you can, depending on how you train it, you can try to promote some of these things. It might be learning sparse coding of subspace coordinates. It might be learning nonlinear manifolds inside this linear subspace. And for us, at least in terms of our angle on this, our research, we're really interested, of course, in the fast feed-forward calculation of those subspace coordinates, which is the same as the spatial factor. So in terms of the scope of the rest of this talk, everything I'm going to show is in the context of an imaging framework we have at Cedars-Sinai called MR multitasking. I won't go into all the details of this. That's a talk on its own. But basically, it's a multidimensional imaging framework. In cardiac, we always do at least 5 dimensions. And so that means that even in our smallest image problem, there's a minimum of 40,000 image frames per scan. We use a low-rank tensor decomposition to handle the cursive dimensionality. But if you frame it the right way, it ends up being a linear subspace, at least from the perspective of the spatial factor. We do use non-Cartesian radial acquisition. So a lot of the spatial encoding is going to look a lot like the other imaging modalities in this room. And even though we've used multitasking for a lot of things, I'm really going to focus on quantitative cardiac MRI in terms of the work today. So I'll go over our basic framework. I'll talk about how we do non-Cartesian subspace data consistency. Some work that we've done, initial work on evaluating, promoting generalizability, and then as well as just a preview of our online implementation. So the basic framework here is that we collect data. We have some specialized sampling patterns that allow us to estimate the temporal subspace from a subset of the data right off the bat. And that means that we can actually back project all of our data into the subspace right away. And so we can essentially get an initial guess of our spatial factor, which is really just a zero-filled filtered back projection. And so we're going all the way from in the first step, we're going all the way from KT multi-channel space down to this eigenimage domain. So in this L dimensional, in this case, I'm going to be talking about 32 dimensional, and that's, remember, in relation to 40,000 image frames. Space. And then we apply our deep neural network in that space to produce the spatial factor that we actually want. So you can look at this as an eigenimage domain network. It's operating on the subspace coordinates. You can also look at this initial back projection as essentially before the network, some dimensionality reduction or feature extraction. It really boils down to being that simple. What you get for all of that is a global temporal model, even with a very small network, because all you have to do is fully connect your subspace dimensions, and you now have essentially the equivalent of a global temporal receptive field. So this is the key to doing that large scale global temporal modeling. So our first work on this was in 2009. This is work done by Yuhua Chen, a UCLA PhD student. Basically, we have almost a couple hundred of T1 multitasking data sets. So that means that there's cardiac phases. So we image motion, 6 respiratory phases, respiratory motion, and we have quite a lot of inversion times for reasons I won't get into now, but there's a reason that we're attached to having that many inversion times. And it gives us 41,000 frames that, again, get expressed in a 32-dimensional subspace. So our labeled images were just reconstructed iteratively from using wavelet sparsity on the spatial factor. That process, at least at the time, this was 4 years ago, took us 20 minutes to do, and we were doing supervised learning. We tried a couple of different network structures off the bat. Yuhua had built this multi-level densely connected network, and we also did some dense U-nets. And qualitatively, just looking at the images, honestly, both structures have very good image quality, at least to my eyes, being able to see the cardiac motion. But you'll note that the reconstruction time, of course, went way down to less than a second. Quantitatively, looking at the T1 weighted images, as well as actually the spatial factor itself. There was a little bit of an improvement in the multi-level densely connected network over the DenseUNet. But what we really care about for this particular application is the T1 maps. T1 is a wonderful non-contrast biomarker for fibrosis and iron and fat infiltration and so many different things in the heart. So this is really the domain where we care about precision and to a lesser extent accuracy. And there wasn't too much difference between them. So this is Bland-Altman comparing against our iteratively reconstructed references. But the precision is something that we'd always like to improve. So we started looking at data consistency, and you will recognize this figure from Matthew's talk. So we have looked at this from the model formulation and trying to look at this as unrolled networks. And so what we want to do with data consistency is, of course, keep the network from hallucinating, make sure it generalizes to some different spatial encoding patterns, et cetera. However, it is quite challenging to do non-Cartesian data consistency. Part of that is computational. Part of that is inefficiency of taking a step due to non-uniform density. And then also how to do this while staying in the subspace. If we have to leave the subspace, then it's all over. There was no point in doing it in the first place. So my PhD student, Zihao Chen, formulated, looking at the subspace DC problem, formulated it 4 different ways. One is to solve this problem with conjugate gradients. One is to do a single gradient descent step. One is a preconditioned gradient descent step, which actually corrects for the non-uniform sampling density. And then one is actually to directly invert that matrix coil by coil, which it's pretty cool. And there was a lot of math that went into it, but basically you can look at encoding as an L by L operation at each k-space point, did a pre-computed inversion, and then was able to apply that in each step. And so all of these strategies stay within the subspace. So it's a 32-dimensional subspace in these cases, so you retain all the computational benefits. So rather than going into all the rows and columns of this, I want to point out that the conjugate gradient, as expected, solves that problem the best, has the lowest error, but of course it is the slowest. Of the single step density compensation, of the single step DC functions, then actually the directly solves, where we pre-computed the inverse, did have the lowest error. This is now looking in the eigenimage domain. Here we looked in the image domain and we saw something similar. Conjugate gradient is going to get you the best answer, but it's going to be slowest. And then of the single step approaches are directly solved, had the lowest error. But as I said, we actually care about the quantitative T1 measurements. And in this domain, we saw something a little bit different. So we started, of course, with our, without DC, we had a lot of room to improve our precision. The directly solved one that had been working best in the other domains actually added some bias and only moderately improved the precision. The best one actually happened to be that preconditioned gradient descent. So even though the image domain and the eigendomain, it seemed like the directly solved was better, we've actually decided to go with the preconditioned gradient descent because, again, we care about the T1 values at the end of the day. There's also some practical issues with the directly solved DC layer. You do have this overhead. You have to pre-compute the matrix, and that changes with step size and can change with motion pattern. There's some scenarios where you'd be able to have the same one from subject to subject, but in terms of the more practical choice, more flexible, we have found preconditioned gradient descent to be useful going forward. So another one of our issues, maybe this is our own problem we are creating for ourselves, is that we have about 1 million different variations of MR multitasking and a bunch of different sequences and a bunch of different contrast combinations, a bunch of different spatial encoding schemes. And we've really been exploring this space. And some of them are newer than others. And we do not have enough data for supervised training in each of these newer variations. So we have a couple of questions we asked ourselves. One is, we know that data consistency helps us generalize to different spatial encoding. So let's see how well that works just with some of our new spatial encoding schemes, looking from 2D to being a 2D SMS, which is simultaneous multi-slice. And then also, how can we shape our network structure, thinking about it as being inside this subspace to promote generalizability to other contrast combinations and other sequences. So the first thing I will show is trying this in SMS. This is again Zahau's work. And so we just right off the bat, when we first had our SMS data, we only had five cases, but we figured, hey, we can try this right away. We picked one of them for validation. All we did was retune the step size of our preconditioned gradient descent VC layer. And then we tried it right off the bat. And actually, the performance between the SMS testing data and the single slice testing data was not statistically significant between them. And qualitatively looking at these, actually quite good image quality. And when we look at our precision and our accuracy, which again is really what we're going to, we see that there was a little bit of less agreement in terms of in the SMS testing data, 55 milliseconds, although that's still going to be good enough for a lot of uses of T1 mapping, but not all of them. And there was a little bit of a bias that was introduced, which is something that we hope to address perhaps with transfer learning or fine tuning in the SMS domain. Now, as I mentioned before, we also want to see how well we can generalize to other image contrasts. And so this is work by Jae-Won Hu, also my PhD student. And if we look at what the actual images look like in the subspace, they are these arbitrary non-physical image contrasts. They're a linear combination of all the images in the sequence. So it's actually these sort of strange multi-contrast, arbitrary contrast images. And even depending on the motion pattern from subject to subject, it can change what contrast gets assigned to, number 2, number 1, et cetera. So what we reasoned was that a network that works component by component on the spatial factor, so the same weights on each entry of the spatial factor, should be learning some sort of generalizable, not contrast-specific spatial feature. So we figured, let's at least see if we can push the network towards spatial learning by removing the temporal modeling, which includes contrast modeling, and really rely on that subspace temporal model and just be doing spatial modeling. And this actually mimics how the labels were generated, because the only regularization we had in iterative reconstruction was wavelet sparsity on each individual spatial component. So this actually is having at least this mimic better our iterative process. So we're trading this temporal awareness of our, what we called the original multi-component network, for additional depth, right? Because now we've saved some parameters by not fully connecting those subspace dimensions in a component by component network. So we decided to do this. We trained on our T1 data that we've been using, and then we just, without any other training, we tested it on the match sequence data, but also tested it on new T1, T2 data that had an additional image contrast that had not been seen at all during training. And this is a lot here, so I'll just sum it up, which is basically that we found that when you remove that temporal awareness, you do get an initial loss of quality, even on the T1 data set, but you can trade it for additional depth, and that brought the image accuracy back. Sorry, I can't do the mouse very well. What we did see was that the component by component network did perform moderately better than the multi-component network on the new image contrast, and that when you actually compare within a network structure across the two testing data sets, the original multi-component network did degrade in quality, but there was no significant difference in performance of the channel by channel network, or excuse me, component by component network. And we saw something similar here. This is the T1 and T2 maps from that new sequence testing data. And we did see that there was a small but appreciable improvement in the limits of agreement in both T1 and T2 just by this simple change in network structure. So the takeaways, I don't think we've solved this entirely, but we have to think hard about what we are trying to do, what we are trying to model with this, with the deep subspace learning, and how it's complementary to what is already being done by the linear subspace. So in terms of translating this, we have implemented this onto our Siemens scanners. We have a little drop down where you can select AI assisted recon in the menu. And then through the Siemens Fire framework, it gets exported to a Python server that's sitting there connected directly to the scanner computer. The raw data is there. It's pre-processed. We calculate sensitivity coils, things like that. We get some preview images in the real-time space really quickly, so we can see these. You give them back to the technologist. They have some immediate feedback for whether or not they got the right slice, data quality, things like that. And then we actually go through and do our binning, create our multidimensional space, pass through our deep learning network to get our reconstructed images. And this took originally 16 minutes with iterations, and we were really even sacrificing on the number of iterations at the time, and brought this down the entire process to 4 minutes, which we see as actually workable. So for the outlook of this, we do see deep subspace learning as a pathway to large-scale dynamic MRI reconstruction in a clinically acceptable time. For the future, we want to get beyond our labels. So we want to incorporate some of the self-supervised learning that Burhan was talking about earlier. That also may allow us to increase our subspace dimension because we don't have good labels for higher dimensionality. And that shifts more modeling to the network, although we will have to be very careful about how that actually impacts our generalizability. We need to do way more robust tests and evaluation of generalizability, more scanners, more vendors, more sites, more patients. And then, of course, the ultimate in terms of evaluating this is to make sure that whatever we're producing actually has diagnostic equivalency to what we were doing before. And with that, would like to highlight collaborators and the people who did this work. Bill, Zahao, Jaewon, and Lei, who really did the implementation of all the stuff that I showed. Thank you very much.
Questions? Actually, I had a quick question. Is this applicable to cardiac like diffusion tensor imaging?
Yes, we find that if you have a lot of diffusion directions and you have a lot of B values, you can get a linear subspace constraint. It's not as efficient as other models for it. I think B values are done better than directions are, in my experience. But again, if you can just do a little bit of gentle subspace modeling just to get your problem small enough as some initial feature extraction, and then you can learn the nonlinearity in a deep learning network, then I think this has a place there.
Questions in the audience?
Just a quick question of curiosity that may be utterly practically useless, but right now you're estimating the temporal behavior with sort of a simple subset of data. Would there be any value in doing temporal learning as well with this type of model?
Absolutely. And some of the other groups who are doing this, I think, have that as an element. I don't know if they're splitting it into from a subset of data or from all of the data. What we have been looking at in this direction is also trying to update your subspace because, yeah, so from all of the data. So you don't have to stay in that subspace. You can update it. You just have to do one more back projection of the original data on there, and then everything else gets to stay in the subspace. So I think there's absolutely room to improve on how to get a better subspace as well.
Thanks.
All right, very good. Let's thank our speaker again.
Thank you all.